26 people, which is nice. So hello everyone. Thanks for showing up. As you know, my name is Jeffrey, but just call me Jeff or whatever. You pretty much know me already. I'll say. So today I'll do D1-3. I'll talk over concepts and do a few questions from Revision Village. Because I think for past papers you can work through it yourself. But if you have any requests for me for questions, like if you have a past paper question that you really struggle with and you want to ask me about it, I can do that. And so by the way, first of all, I just want to apologize in advance for if this session sounds poorly planned, because as you know, I'm also taking my exams this May, and so I need to revise myself. And right now it's 11 p.m. over here. So if I'm not being clear, please let me know and I'll try my best. Fuck, I can't read the chat. So let me see. I can't. So unfortunately, I don't think I can check the chat when I don't think I can check the chat when I'm typing on this. So I'll need to do things like this. So what I'll do is I'll make my status online, and when I'll make my status online, and so if you have a question for me during the thing, you can ping me, and then you can ping me, and then yeah. Oh God, no, never mind. I'll just whatever. I'll just check the chat once in a while. So yeah, again, so I'll start now. So I'll just talk about the concepts and then do a few questions from Vision Village. So I'll start with D1, which is gravitational fields. And just to confirm, everyone can see my screen right now, right? Like the Microsoft Word. Okay. So the first thing about D1 is talking about Kepler's laws of planetary motion. So there are 3 laws about it. I'll just state it because you pretty much don't need to know how to derive them. Only need to know maybe derived third law. So for first law, all planetary orbits are elliptical. And that's kind of like an empirical observation, right? Like Kepler a few hundred years ago just saw that planets orbit in an ellipse, but he doesn't know why. And then later on, when Newton published his physics paper, he derived this. But then this is essentially a first law. Second law is that the area swept out by a planet in orbit per unit time is constant. So just to illustrate this, if we have a sun here and an elliptical orbit here, then in equal amounts of time, then so let's say these two areas are swept out in equal amounts of time, then these two areas should be equal. So can everyone see the diagram here? Okay, got it. So this is second law. And the third law is that time for a circular orbit, t square is proportional to t square. The time period of orbit squared is directly proportional to the radius cubed. So you for the third law, right? It technically also applies to elliptical orbits, but for IB, you just need to know that for a circular orbit, this is definitely true. So that's Kepler's laws. And now we move on to Newton's law of gravitation. So that's kind of how we start off. So gravitation. So Newton's law of universal gravitation essentially states that every pair of masses experience an attractive force. So my physics teacher used to joke about how like don't use this and joke about people being attracted to each other. So the equation for this is so the force is equal to g m over r squared, where m and m are the mass of the two objects, r is the distance between them. So note that f is a vector, and so then you need to consider the direction of the gravitational field, and also understand that it's attractive. So don't have so when they ask you on gravitational fields, please don't write something that says gravitational fields repel masses. And that's essentially the one key equation you need to know. And essentially, when a planet, let's say, is in circular, when a planet is in circular orbit around the sun, an orbit around the sun, then it experiences a force of F equals g m over r squared. So that's that. And so we can technically use this result to derive Kepler's third law, because we can use this to derive Kepler's third law for circular orbit, because you can know that the centripetal force equals to the gravitational force. Then you get then after some algebra you get and not mv squared over r. And then after that you get m omega square r equals to m 2 pi over t square r equals to g m over r squared over r squared, which rearranges to t squared equals to gm over 4 pi square r cubed. So that's that. And just one final note is that gravitational forces are equal and opposite per Newton's third law. So let's say if we have two arbitrary masses, let's say if we have two masses just randomly, then as mass 1 attracts mass 2 also attracts mass 1, and the forces should be equal and opposite. So just remember that when you're doing questions. So that's Newton's law of gravitation. Wait. God damn it. Um, wait, sorry, 1 second. So now we're talking about gravitational fields. So here is one important thing about all fields, right? The principle of superposition is that the resultant field of um, multiple objects is the sum of the fields from individual objects. So what do I mean by this is that let's say you have at some point you have one object that has a gravitational field pointing this way, and another object whose gravitational field is pointing this way. Then the resulting gravitational field will kind of point this way. And it's just kind of like vector addition. So let me just check the chat real quick. Okay, not much going on. Okay. So that's that. So remember this principle of superposition, and this applies to all fields, electric, gravitational, magnetic, etc. Make sure you keep this in mind when solving fields problems involving multiple bodies. So that's that. And so what happened? So anyway, now I've talked about superposition principle, and I'll now talk about gravitational fields. So the reason why gravitational fields exist is that sometimes when people talk about force, they talk about, okay, but the force involves two objects. Can we perhaps come up with a quantity that is only dependent on the mass of one object? So there comes gravitational fields. So it's a quantity that is dependent on one object only. And so they're saying how, okay, let's say if force is equal to gmm over r squared, then maybe we can define the gravitational field strength as the force exerted by one body, force per unit mass exerted by one body on another. So equals to F over m in that case, because that's how it's defined. So then when you divide this equation by m, then you get gm over r squared. And just note that gravitational field's strength is a vector, so that I technically should have a vector sign here. Is a vector and it has units of acceleration. So technically speaking, you can also think of it as the acceleration experienced by a mass in one point of a gravitational field. So just as a simple exercise, calculate g of Earth. So I'll give you 2 minutes for this. So we know that so g equals to so I'll just give you 2 minutes to do this. So some key data is that g equals 6.67 times the mass of the Earth equals to 5.97 times 10 to the 24 kg on radius of the Earth equals to 6370 kilometers. So can everyone just do this real quick? So just to see. So just spend 2 minutes, and when I see, and so just kind of verify that G equals to 9.8. So you should get 9.81. Well, yeah. So is everyone getting this so far? Yep. Okay, then I'll move on. So when drawing, apart from calculating gravitational fields, you also need to draw gravitational fields in some problems. So when drawing fields, you need to know that the field lines must be field lines indicate the direction of the force exerted when a mass is placed there. Field lines must from a body must be perpendicular to its surface, and field lines cannot intersect, because that implies two different forces for the same point in the field. So just to demonstrate, so let's say we have a gravitational field from the Earth, then the field lines should look like this. So I'm drawing the things normal to. I'm just drawing the fields normal to the surface. And they should be quite. They should be quite clear. They should be straight lines, and the arrows should point inwards because the force is attractive. So does everyone get this so far? Okay. And now here's one. And now I want to ask you guys a question then. Let's say we have two. Let's say now we have two bodies. How would you draw two bodies of equal mass? How would you draw these field lines? Two bodies of equal mass. How would you? So this is something that I want you to think about. At some point, it will cancel in the middle. That's correct, because yeah, go on. I use touchscreen Peacock. So some solid guesses there. So for a gravitational field from both, so let's start from easy, because in far side you kind of know that they don't intersect with each other, so they don't kind of mess with each other. But then towards the center, there's no field in the middle. So what happens is that there's no field in the middle, and the lines kind of stem out from here. So this is kind of what happens. This is kind of like what happens if you have you sketch the gravitational field of two so this is just one extra thing you want. So y arrow is pointing up. Oh, sorry, my mistake. My mistake. Sorry. They should point. Sorry. Sorry, but you get the point. You get the point. My bad. Only one though. Yeah. Yeah, my bad. So I will come back to field lines later, but you kind of get the gist of it. And I don't think IB has that annoying like field lines questions. Like I remember seeing one question where they have like an Earth surface like this, and they ask you to sketch the field lines, and then well that's easy. So you just draw like this and then jump done. So as just a final remark, field lines are further apart when the field strength is weak. So that's that. And so that's how to sketch gravitational fields. And later on, when I talk about the HL, I'll return to it because then I'll talk about equipotential surfaces. So, but that's all. And for D1 SL, you also want, and actually that's all for D1 SL. So with that, I'll just give you another problem. Actually, that's D1 SL. So now I'll go on to Revision Village and do some problems. So first of all, we have this problem here. Should be quite easy. Can everyone see it? Can everyone see a problem? So we have this problem right here. Is an MCQ. Should be quite easy. So what's your answer to this? I'm getting a lot of B's. I'm getting a lot of B's. B is correct because Kepler's second law is basically just equal area swept out in equal amounts of time. Split screen. Oh, I don't know how to split screen, sorry. Um, I'll now go to another one. Like this? Ah, I see. So, okay, let's now try this. There we go. So let's now try this question right here. Oh, hello. So okay, so now let's try this question. So should be quite simple as well. So can everyone just have a go at this question? And everyone can see it, right? Yep, so have a go at this. Hmm. What problems? Yeah, no, you don't steal my router, come on. So I'm getting mostly B's. Mostly B's. So people are a little bit split by this question. So it's actually B. Because it's actually B. Because what happens is uh G is as so I am cruel said it right. G is the acceleration, so it should be independent of mass. And the reason why they say h is small is because they just want to treat that GE is constant. The G is constant because when you get to very, very high altitudes, then G starts to vary and you get different accelerations. But in this simple case, you have the same gravitational strength. So in other words, you get the same acceleration that's independent of mass. So I'll move to a harder question now. So here's one more. Now try this one. Now try this one. I think this isn't as conceptually easy, but I think if you have a really good think, then you should be fine. Actually, I haven't. Okay. I'll wait for a few more responses first. I'll wait for a few more responses first. What's the hardest question you've seen from RV? I actually don't use it that much because I actually don't use RV that much. So chances is when we get to longer questions, I might not have done it before. So like if we get to a question that if we get to a long question, I might have to do it on the spot. And that's that. Do you go to SJII? What's SJII? So I'm getting mostly C's, so C is correct because because it experiences the centripetal force as the Earth. Wait, what's SJII? I actually don't know. What's SG? I actually have no. Oh no, I don't. I don't. I'm not from Singapore. I'm not from Singapore. Why is everyone assuming I'm from Singapore? I'm not feeling good, bro. Stop. I'm not feeling good, bro. Like, come on. Stop. No. Stop asking about my school. Otherwise, I'll cancel the session. Uh, just as a simple illustration, so here is the Earth, and you have a satellite here. So as the satellite orbits the Earth, the astronaut inside also orbits the Earth. So the astronaut also experiences a force from the Earth. So that's the simple explanation to why one is wrong. So does everyone get it? Yes, I plan on studying physics. Come on, mods are here. So let me see. Let me see. Is there one more question? And I've one more longer question, or like one more longer question, and then like um I will stop. Okay, so let's try this one. So I've just gone through this question, but give this give this question a go. Okay, chat solve this question. Yeah, I mean that's how it works. There's like what happened. I think what happens if you become too static is that you start not taking things in well. What's that? Okay. What should happen? Let me. Nothing happened. So we're going through this MCQ right now. It should be quite simple. Well, you need to know that I can pretend accent really well. Should be quite simple. Oh, day. I saw day. Some days. Some. So I got some days. Some says. I don't know. Dates. So please have a go at this, and then I'll reveal the answer and then discuss. Okay. I'll wait for dreams to. I'll wait for. Guys, let's focus here. Yeah, please. Your exam's in 10 days. Come on. What's the formula for force in A2? F equals M A. And mv squared over r, or m omega squared r. So okay. So the answer to this should be C. Oh, it's actually D. Never mind. It's D actually. Never mind. Then I made a typo. My bad. Mm, I probably made a typo here. So I'm very sorry. Uh, I mixed up the denominator. I see. No idea. So here's the explanation. So you just essentially it's just equating the centripetal force to the gravitational force, then doing some algebra, then you get this equation. Do we need to remember Kepler law formula? Yeah. So I think you just need to know that p squared and r cubed are directly proportional, but I say it's useful that you remember this coefficient as well. 4 pi over g. I think just dimensional analysis. I think the mark scheme is right. I think the mark scheme is right. I think it's the mark scheme is right. Just check the units. Just check the units of the just check the units of the whole expression, and then like I think the mark scheme is right. So I made a mistake a while ago. So I'm sorry. I'm very sorry. Yep. Just as a remark, so Rack, to answer your question, so the units of G is kg. So then the units of gm is then m cubed s negative 2. So then if you then multiply gm by, so then like when you have, so then if you flip this fraction, then like your formula will probably be wrong. Yeah, so then gm times t squared then will be m cubed Do you get it? Yes, I will. I will solve. I will share it. Rack. Yeah, this should be correct. Yeah, this should be correct. So I think that all is well now. So let me find if there's an SL only question because this is an HL resource. So you see how sometimes they might ask you to derive it. Okay, let's do this one as the last question because I want to move on first. This is not only SL, but I'm doing the so when I finish the SL parts, I'll do some questions and then I'll move on to the HL parts. So right now I'm doing SL only. And then after I finish like one more question or two, I'll move on to the HL parts. No, we won't do D4. By HL parts, I mean like the HL parts of D1 and 2. When the exam? 10 days from now. Okay, so can everyone give this question a go as well? So chat, this is the last question I'll go through before I move on to the HL parts. So chat, give this question a go, and then like after this, I'll move on to the HL parts because yeah. Okay, sure. Oh, I have my answer. And SL could be defined gravitational field strength. Yes, absolutely. So gravitational field strength is inversely proportional to r squared. So I'll give 30 more seconds and then I'll reveal the answer and I move on to HL. I need break. After I finish, okay, so after I finish D1, I will give everyone a break. What do you mean does visuals come into part here? No, don't do it. Like every time the disclaimer diagram not to scale exists for a reason. And also how are you gonna and also you by eyeballing you're also assuming a constant like the same density which is not true. Yeah, so I got yep, so I get Ace, which is correct. So so uh so the answer is A, and I'll just I'll just have this out real quick so everyone can look. So this is just basically equating the two gravitational forces and then kind of rearranging to get m1 over m3. So please yeah, so here's the explanation. I will move on when you guys tell me it's all right. I think we should know the great boundaries for a whole. Why do we do x minus d? Because when we are doing the distance between these two objects, when we're calculating the force between m2 and m3, then we need to do x minus d, because that's the expression for the distance between m2 and m3. Yes, I did 2D as well. I think this kind of I think the RV mark scheme kind of overcomplicated. Yes, 2D is completely fine because this essentially means 2D. So, come on. Okay, right? The grade, but even if the grade boundaries change, the percentage of people getting a 7 won't change. Okay, that goes for good. Sure. So, if if you get a very low grade boundary, then chances are the paper is either hard as shit or everyone fumbled, then everyone cried. So maybe if the paper, maybe like if I don't know, maybe if like, oh my day, what are you doing 10 days before the exams? Revising for a bunch of shit. I have 2 language A's and London. Jefferson IB. I'm an IB person. Yeah, and I take math HR. Why? And okay, so I'll take it that everyone's ready to move on. So I will now. So HR part starts now. I'm AAHL. Yeah. Uh, historical figure just goes. Um. Okay, so everyone can see this well, right? Okay, so D1HL. No, I'll start D1HL now. So for D1HL, now one of the main focuses for D1HL is then energy. So we want to talk about gravitational potential energy. So why would we talk about gravitational potential energy in the first place? It's because we want to see, right? Um, defined by. So we want to see, right? How much energy does it take? How much energy work needs to be done in order to move a mass from infinity to a point in the field? So that's that. So that's how it's defined. So when you have a gravitational field, so when you have a gravitational field from here, let's say you have a infinitely far away, you have a mass and you want to move it from here to a certain point that is a distance r away, and then we want to, and gravitational potential energy is how much work needs to be done. So does everyone get this concept of why does this quantity exist? God, I'm kind of lagging here. Do the work done as work done by the field or work done against it? Uh, I so as so so I don't know why it's defined like this. So because I'm thinking of a good explanation here. So I think a reason why this is defined is because field store energy. Field will store energy. So energy terms need to be defined because work will then have to be done by or against the field or an object inside the field. We're not discussing why it's negative. We're just discussing why this quantity exists. So that's that. So I'll just throw out the formula straight away. So GPE. So the gravitational potential energy is equal to negative GMM over R, because this is derived from the work energy theorem. So so this is how gravitational potential energy is defined, and mostly when you're so let's say when we're finding a gravitational potential energy of some mass in some field, a distance r away from some object, then we just plug in this formula and it'll be done. And I'll talk about some more applications later on. And so now that with gravitational potential energy, we also want to talk about gravitational potential, because let's say now gravitational potential. So the reason why this quantity exists is the same kind of the same logic as why gravitational field strength exists. Is that because the potential energy is dependent on both masses, then people will say, can we have some quantity such that the gravitational field strength, such that it is only dependent on one mass, and so there comes gravitational potential. So define as the work done. Yeah, okay. I'll talk over this point and then I'll go through the negative part. Work done per unit mass needed to move a mass from infinity up. So because force is attractive. So this is my simple explanation, and just to explain it further, right? So let's say you have a gravitational force here, and then you know how when you're into field, it starts to get attracted. So let's say your hand is holding a mass, and then you're kind of moving it closer. then like your hand kind of gets dragged with it. So then like actually work done is being on your hand and you're not doing any work on it, but then work is actually done on you. So that's why the negative exists. Sorry if it sounds kind of confusing. On the mass by the CYZ, GPE is not only for objects within the atmosphere. No, I said work done per unit mass for gravitational potential. I did it. It's not the same definition, so I'll highlight it just in case. So I'll just talk a little bit more about the negative because this is something that you need to know. So for a little bit more on the negative, implies that work done has to be against the field. That work has to be done against the field to free the object. So therefore so then we can consider bounded. To be on silence. Can you say a resultant type force? What do you mean resultant type force? So for example, so just as a more clearer illustration, right? So let me just delete these. So let me just as a clear explanation. So let's say we have a sun and then we have some planet, just some poor planet orbiting. And so technically it'll just orbit and orbit, go round and round and round. So it can't go wherever it wants, right? So to free it from keeping going round and round, we need to put some work done to free it. So then we need to put some work done. So work is needed. Work done. So work done is needed to free the object. So it won't. So this poor guy won't keep going round and round along this big mass. So that's kind of why potential energy is negative. Is because it is kind of trapped. Yeah, I think that's a kind of good way to know. Yep. So um, so as you said, just as some equations. So the gravitational potential equals to negative gm over r, and then so the work done will be equal to the change of gravitational potential energy, which is equal to m delta g. So that's that. Well, force of gravity does not no work on satellite when it's in orbit because because it's centripetal force. So because the force is perpendicular to the, so let's say the satellite is in a circular orbit, then the force is perpendicular to the satellite's velocity. And using the work energy theorem, you then get that the work done is zero. Equipotential surface. Yes, you can look at it that way. If it's in if it orbits it in a circle, then like, and we approximate Earth as a perfect sphere, then yes, we're gonna also talk about how it's on an equipotential surface. So okay, so I'll move on now. So that's how you define gravitational potential, and now we move on to equipotential surfaces. So this is defined by surf. Why does it keep being fixed to bold and underline? This is so annoying. Surface is with the same gravitational potential. So when drawing equipotent. Oh, thank you. So for equipotential surfaces, right, there's two things that you have to consider. So first of all, equipotential surfaces are perpendicular to field lines and are further apart when the gravitational um field length is low. So that's the two things that you need to keep in mind when you're drawing equipotential surfaces. So I'll do some wrong illustrations here just to show how it works. So so here's one wrong illustration. So here comes the first wrong illustration. So I have a planet here. We have some nice field lines. Sorry if they're not perfectly perpendicular. And we have like So what's wrong with this equipotential surface? Yes, I'm doing a wrong example. So yes, not circle, that's correct. If you have a spherical planet, then equipotential surfaces should be spherical. And yes, they're not perpendicular to the field lines. That's correct. So here's a terrible example. And I'll do another wrong example before moving on. So here again, some field lines. This time we have this. Let's say they're circle. What's wrong with this? So okay, right. Good catch about the distance between equipotential surfaces. That is correct. But then they shouldn't be equidistant. They should get further and further apart because the gravitational potential becomes less and less as you move further and further away from the planet. So a correct illustration should be something like, I hope I don't botch this. A correct illustration should be something like this. And something like this, where like they get further and further apart alongside the gravitational field line. What if they're two, would the in between not be equipotential? Yes, it will be a bit harder if you have two masses. So let me just do a quick search. So for two masses, it'll look something like this, the equipotential surfaces. But then just make sure they're perpendicular to the field lines and get further apart, and it should do the job. And yes, and good catch, that is the same for electric fields. So yeah. So I'm cool. Does this answer your question? I changed okay. I think when you sketch equipotential lines, you don't really have to be very concise, but like keep the rough shape there. So here we are. And just a remark, sorry. One more remark about gravitational potential is that it it, it is also defined as is that gravitational field strength is defined as the negative gradient of the gravitational potential. So so yes. So okay, so I won't talk over this because it's 12 midnight and I'm still on D1. Yes, there'll be break after D1 and I'll do some fun stuff. So because when you're on equipotential surface, the energy is the same. So the gravitational potential energy will then be the same. So when you move across an equipotential surface, there won't of it. Yeah, I've stayed up for a few. Yeah. Can I do rigid model mechanics? Peacock already scheduled one. So anyway, here's equipotential surfaces. And one last thing for D1 HL, and then we'll do some questions and call it a day. So, for D1 is orbital and escape speed. So I'll talk about them together because they're kind of similar. They have like similar logics, I'll say. So orbital speed when the centripetal force of the equals gravitational force in a circular orbit. So then the orbital speed, I'll just fill the formula v or equals to square root of gm over r. Oh my god, I hate this. So we're orbit. So yes, so derive. So for the derivation get mv square over r equals to gmm over r square. Then after some algebra, then you get v equals square root of gmo over r. So that's that. And for escape speed, is when total energy equals 0, because this is when the object becomes unbounded. Because remember, right, when the energy is negative, then what happens is it's trapped within the orbit. It can't escape. Velocity still in the syllabus. Drift speed is removed, but I have it in my mock because I think it tests your modeling skills. So so what happens is then um um the escape velocity is equal to square root 2gm over r, and we'll just set it by 1 over 2 mv squared minus gmm over r equal r equals 0, then you get this result. So that's that. And one last extra detail I want to not in magnetic field, but yes in electric fields. So guys, please focus. One last thing is that you'll know that after some algebra, you should realize that the total energy of us object in circular orbit is equal to the negative kinetic energy. This implies that as the orbital radius decreases, then KE will increase whilst P and total energy will decrease. That is yes, Ange, that's correct. So here's the last point I want to make about this, and then now so just take some time, and then because that's D1 done, and then I will do some questions and take a break. Do you have a question for this? If a spaceship turns out it will drift around orbit. I think so. Well, I mean, if how long's my break? Around 5 to 10 minutes. So what I'll do in break is I will play one GeoGuessr round or two, and then you can watch, or you can just take a break, or maybe do some questions, or just kind of digest what I said, that kind of thing. Yeah, make a lobby. No, I won't. Sorry, because no, I won't, because otherwise it'll take too long. I'm very sorry. Maybe one day when I become event host, I will. Yeah. So I'll tell you later. But then no, I'll make a lobby another time. So now we'll go on RV. Potential decreases and K increases, right? Yes. Because total energy. Yes, so I say, yeah, that's what I said. So when orbital radius decreases, then KE increases. So you're just saying the converse, right? So when orbital radius increases, then yeah. We're sleeping tonight. Yeah, I'm not sleeping as well. So anyway, I will now do one MCQ and one long question. So here's the first MCQ. So question 37. So I haven't seen this question. I'll also do it on the spot. Okay, so question 37. So spend some time. I think I'm going. Actually, this question's SL. I should have done this earlier, but okay, please focus for a bit longer than like we can lock out for 5 minutes. I do. Okay, so yep, have a go. Hide your answers and spoilers, and then like I'll do one more long question, and then we'll take a break. Okay. So I'll have so okay. So majority is D. Majority says D. So D is not correct. I also got D. This is funny. I think this is a typo. Chat, I think this is a typo. Why did they substitute in 3r squared? I think this is a typo. I think D is right. I skill issue, revision village, GG1, I get out. Let me see. Oh wait, never mind. I think I know what I know. Oh wait, right, never mind. Wait, no, never mind. We all skill issued. I also got it wrong. Yeah, right. MB. Oh yeah, I also skill issued. My bad, my bad. Yeah. Yes, you're right, Edon then. Yes, I also didn't notice this about surface. So you see, I also make mistakes. Yeah, so I also got it wrong. Don't worry. Uh, so I'll now do a longer question now. So let's try this one and then let's take a break because wait, can we see solution? Okay. What? Yep. So yeah, basically substitute in the wrong thing, then GG the whole thing. Ratio of centripetal force in Oscar. Yes, yeah. I think we also yeah. So that's why when you do with planets, please pay attention if it's above the surface, because otherwise you end up like me, revision host getting cooked by medium difficulty. So I'm lagging a lot right now. I'm very sorry. So mm, actually, let's just do something easier. Mm, Let's do this one. Wait, my bad. Let's do question 41. All parts. This is just 5 marks, so it should technically take like 5 to 7 minutes, but I think for part A it's just substituting numbers. Break will come after this question, yeah. Yep, so give this a go and then I'll show the answer and then we'll take a break. And- Okay. Actually, I think part C is a bit tricky because some people might forget one minor detail that will change their answer. I think this. Yeah, well, don't worry about the keywords because like I'll go through the mark scheme and then like you can't see like what kind of terms you need to throw in anyway. So just I think a rough idea of how to answer this will be good enough. And I'm sorry if I'm not doing enough questions because I want to talk about the concepts. Maybe when have you done Andrew's mocks? No, but I plan to do it. Well, okay. For part C, you need to say does it increase or decrease? How does it change? Not why does it change? Okay, I'll assume most people are done. Yes, last question before the break. So I'll so I'll focus on part C because that's where most people got it wrong. So the gravitational potential will increase because yes, Vinny, you're right. Because you need to realize that if the GPE is negative, so then when you increase the R, the potential becomes less negative. It becomes less negative. So then the change in potential is actually positive. Peacock. Trust the physics, not the majority. I always round up the answer. Round it off because I think what happens is IB will give you a leeway, or I trust that. Not three sig figs. Usually it's the least, not the IB convention is like the least number of sig figs. So in this case, they gave two sig figs, so you round it to two sig figs. But then usually you won't get penalized for sig figs unless if they really clearly tell you that will you. I think session will do. I'll see when we end because what happens is right now it's 12:30. It's now 12:30 a.m. for me, and I still have D2 and D3. Nature of science. I think for nature of science. Sometimes I'm go back. Well, my biology clock doesn't here. D2 shouldn't take that long. No, I need to explain magnetic fields. And then you also need to consider that electric fields are directional because there's positive and negative charges, and I need to spend some time talking about that as well. So that's that. So is everyone good with it? Sis, yeah. Yep, sis, congrats on getting everything right. You don't took it. Isn't needed. Well, I need sleep because I'm getting increasingly stupid in physics Olympia. So, okay then. D1 over. So please come back when. So now I'll have a game of GeoGuessr. Or I'll play World. Why not? But then I'm only playing for like 1 or 2 rounds, so you'll need to be back quite quickly. Yeah, and Rack, please help me keep them in check. Yeah. So, yep. Well, I need a break. Everyone needs a break. Which, oh, you know what? I just want to play some speed. Somewhere in Tokyo. Oh my god, I'm lagging. Aspetta che sto vedendo. Lordesta. No, I'm thinking Brazil as well, but like, let me take a closer look. I think it's Brazil. Oh, I'm playing GeoGuessr right now. I was fucked. Probably some part in Eastern Germany. No, Central. Never mind. Okay, let me try find a road. Let me try find a road. Oh no, I'm lagging so hard. You know, finding a road is stupid. We're in America. Yeah, but everywhere in America looks the same to me. I can't lie. Metro. You know what? If I'm taking a blind guess, I think Florida. I think probably West Coast. What is this? American sidewalk, you sure? I mean, I did see some English. Peninsula. No, it's Australia. Bruh. I'll play again. One more round, then I'll be back. I think it's somewhere in. Bruh. I got caught. Well, Shadow, you need to know that I've been talking non-stop for 1.5 hours. Yeah, looks India. I think looks northern India. I think not too bad. Bungus. I think looks Southeast Asia. Oh, Indo-Rupia. Indo. Oh, thanks. These houses look kind of American, but the sidewalks look kind of British. Yeah, looks too sunny. Yeah, looks too sunny to be British. Someone said New Jersey, so I'll trust you. Oh, good call. Looks European. The grass looks Polish. Yeah, I think like it doesn't look Western Europe. And I don't think it's Russian. Oh yeah, Poland. back to work. Someone ping. Someone back to work. So let's see who's in the call right now, because now we're going back to work. So D2. I have a job to do and I need to sleep. Yes, I will send this out later. Hold on, something, let's see. Is there a schedule? No. Yeah, I'll rename it. My bad. So I think for D2, the first thing. So okay, yeah, lock in, please, quickly. So for D2, right? So electromagnetic fields. So for electromagnetic fields, the first concept that you need to be familiar is the concept of charge. So I think all of you are familiar with charge. So charge can be positive or negative. Opposite. So if you don't know the concept of charge, then I pray for you. Then one more thing that you want to know about charge is that charge is conserved. What is charge? Charge is just a fundamental quantity. Please don't joke. I can't take jokes. Oh, okay. So that's all you need to know about charge, right? So positive is protons, negative is electron. I think all of you know it. Then calculate the concentration of charge. Maybe, I don't know. Please don't joke. I'm being serious. I think it's transferred, at least in the scope of IB physics. Charge is always transferred. So for charge transfer, right? So even though charge is conserved, you can still transfer charge, right? So there are four ways. There are a few main ways, right? Of charge transfers. I'll say transfer, not distribute charge. So, but you charge something by friction. Charge something by induction and contact. So friction, when you rub an object, you might rub off its electrons. Then the I will be nice if you're nice to me, right? Can I place a hard question here? Not yet. I will answer later. I'll answer when you do D3 because I want to hurry up. So friction, induction, you bring a charged object near then the I have no idea. So so just as an illustration of what do I mean by charge by induction. So let's say you have a balloon here and you have some positive charges. If you have an object here, then the negative charges will attract to the positive charges, and the positive charges will be repelled by the balloon. So then the charge is then redistributed. So do you see what I mean? Yeah, Gab. I think Gabs is recording it, so that's fine. So that's induction, and for contact, then so by contact, then charting by contact is just quite simple. So for example, if you have a metal sphere here, and you have a charged rod, and you get to it, then like some charges kind of get redistributed on the ball, that kind of thing. So that's charge by contact. And then one more thing. What's your average? I might not be free. So, and one more thing about charge transfer is that you want to be kind of grounding is because how the Earth is roughly neutral and has a lot of free charges. So then, therefore, when you connect a charged object to the ground, it can discharge through the Earth. So for example, in some really tall skyscrapers, the reason why people inside really tall buildings don't get electrocuted is when the lightning strikes, there's a very high pin up here, and then like it kind of brings the charge to the earth. Sort of like the charge just flow into the earth because when you kind of ground something, then because earth is a very neutral thing and it's just so big that like it can just kind of take care of these excess charges. Yeah, it's massive. So that's that. Uh, and I think that's about charge transfer. So the first thing I'll talk about is electric fields. So it's the same as gravitational field, so I'll be really, really quick about this. So electric field is just defined by um fuck. So KQQ over R squared. So then K is Coulomb's constant, so K equals to 1 over 4 pi dot. So that's that. Uh, um, I, I don't want to talk. I don't want to include units because I'm just lazy. So remember, right? So positive like charges repel. So positive F vector means a repulsive force, and vice versa. So just remember that. And and remember, right? This formula is only applicable to a vacuum. In other media, then there will be another equivalent K. A change in payment. Uh, where epsilon is the permittivity of the material. Medium. So that's that. So let's say if you have two point charges in olive oil, then the force between the 2 point charges will be different to when you have these 2 point charges in air. So keep that in mind. So that's electric fields, and then actually no and then similar to how gravitational fields is defined, then we can also have electric fields. We can also have an equivalent to gravitational field strength of electric field strength, which is just E vec equals to kq over r squared. Notice how it is negative. So please, when you're doing electric field strength, then you will need to notice that the direction will be different. And one more remark is that between parallel plates of unknown potential difference, we can also use the formula E equals V over D. Plates. So that's something you know. You don't need to know why this stands, but it works. So to sketch. Sketching electric field lines is the same as sketching gravitational field lines. However, pay attention to the charge of the object, because it will affect the direction of the field. Yes, so I'll illustrate it. So for a normal point charge, then the field should go something like this because it's positive, right? Oh yes, that's how it's defined. I'm sorry, I'll add that later. Um, and for parallel plates, then again these lines go from positive to negative. It should look like this. And I guess on the edges, then it'll have some edge effects. But it'll look like this. And then you can see the field is uniform, right? And again, because and just like gravitational fields, when you are as the field strength decreases, your field lines should be further away. Is the field strength uniform? Wait, this point, please. Yes. So okay, so the reason why the field is uniform is beyond the syllabus, but I'll just add a remark here. Full for full up on Gauss's law. Why do you know all of this? Well, I do a lot of physics. That's a simple explanation. So that's that. I'll just talk about force per unit. I need all this plus charge per unit for positive charge. That's a point in the electric field. So that's that. Experiment involving the rod and balloon are neutral. I don't think it really matters. Wait, come on. Please focus. So now one more question on sketching field lines, right? How would you sketch the field lines between a positive and a negative charge? So let me just answer Carol. So yep, you're correct. So it goes from positive to negative. Remember, right, the field lines should be perpendicular to the surfaces, so keep that in mind. And I guess when you go away, then and notice how for the negative arrows, you have the arrows pointing towards the charge. And for positive, you have the arrows pointing away from the charge. So, any questions? Why are you teaching Fox, by the way? I'll host D4 in another time. Oil drop. Yes, I will go through oil drop. Yep, and let me think. Is there anything else? Yep, so now I'll go through millican oil drop experiment. So this, you need to know about this. So you must know about the millican oil drop experiment. So it's an experiment conducted by Millikan. So the experiment is basically him dropping oil of different masses in a parallel plate electric field. So for the Millikan oil drop experiment, what Millikan did was he the basic setup is that you kind of have an oil drop down here, diagram not to scale. Then just parallel plate, bottom negative. I forgot, but it essentially is the same idea, right? He produces a experiment where there's a uniform electric field, and then my bad. Field forces static force equals the weight equals the weight. And like for the millikan, yes, the oil particles have to be charged. This so I'm just going for a basic idea. So I'll neglect buoyancy for now, but like you can make a correction for buoyancy. Yeah. So then, what the key takeaway for Millikan oil drop experiment is that as Millikan varies the mass of the oil, he discovers that charge is quantized, and so therefore we have this quantity called elementary charge, which is E equals to 1.60 times 10 to the negative. Fuck. Nothing coulombs. Okay, so there we go. Balancing of forces. Okay, so what happened? Okay, so when the oil is dropped through the electric field, then can you now explain? So the oil is charged, minus in this case. The oil is charged, So when it enters an electric field, there is a force acting on it. And the force should supposedly be yes, so it repels from the bottom. And then so it repels such a way that the electrostatic force will be exactly balance the oil drop's weight. Yes, correct, Rack. Yes, so it's basically just exerting an electric force such that the weight will be cancelled. So if you have time, look up this setup and and the specimen HR paper 2 also has a question based on this experiment. Not necessarily, because Q equals energy is when you ignore buoyancy, but then you can also account for buoyancy. When the weight is cancelled, then the oil just floats there. I think, have I done a specimen? I think so, yeah. Yes, it floats between the two plates. I don't know if the oil is positively or negatively charged, but then I kind of forgot. But then the idea is that electrostatic forces balance the gravitational forces. Oil drop question was very confusing. Sure. Sure. Is it for the specimen? I'll I'll look it up right now. Actually, I have a. Look. Um. Really? Okay, so paper 2 in it. So I'll scroll down. Did you mean this question? Okay. Mm, this one? This one? Hmm. Yeah, well, I think what happens. Yeah, I know. I think what happens is that because. Let me check the mark scheme because I kind of forgot how the So which part did you not get? Did you not get this part? Yeah, because so this okay, charge is quantized is a fact. Well, because the charge on this whole oil drop is 3e, and then you I think the question wants you to notice that this is equal to 3e. So then yes, it's not a formula. You need to know that you need to know the quantity of the elementary charge. Mass equal. Yes, you need to notice that is 3e after you find out the charge. Uh, yeah. Not conservation of elementary charge, it's quantization of charge. There's no such thing as conservation of elementary charge. It's either conservation of charge or quantization of charge. Yes. Elementary charge is given. Yes. So yes, so then they just want you to notice that this exists. Okay, so I'll move on now because I think everyone's getting the hang of it. Yeah. So now here's a final SL topic and then I'll do some questions. Is magnetic field. So magnetic fields, as you know, magnetic field. So magnetic fields have north and south poles, and field lines go from north. Can I explain what one last So then they basically I'll type it in chat, right? The question basically wants you to realize that the charge equal to field. Okay, so field lines go from north to south. Cool. A few ways that magnetic fields can be produced. Moving charges on ball magnets, current carrying wires. So for bar magnets, so okay okay, sure. So for a so I'll just sketch the magnetic field lines for each scenario. So for let's say we have a north pole, have a south pole here, then that's easy. Just draw field lines like this. E is electric field strength. Yes, so because remember, right, the whole experiment is when you have a droplet of oil and then inside an electric field. So then there are electric forces acting on it alongside weight and drag force or buoyancy or whatever. So that's that. Drag is against velocity. It's not necessarily against other forces. Okay, so for bar magnet, so from north to south, then you just go like this. I'm just going really quick. Something like this. So from north to south, something like that for ball magnet. I need to be great. Can I move on to my bad, bro? Yeah, but magnetic fields from north to south. Actually, let me see how many people are still in this. So 18 people. Okay. Okay, then Okay, then so bar magnet for north and south, and then for current carrying wire, then as you know, you'll have the right hand grip rule. So it has a circle, and then like the field lines should be further apart with the new. Um, wire use. You actually don't need to know it, but then um, but dreams. So this is what you mean. I was so confused when you're saying you said curve for a straight wire and like what? I thought you were joking. You should just say magnetic field produced by current through a straight wire. Okay, so so for a straight long wire, you have you have oh I learned it right before the session started. So mu naught so then mu naught is the permeability of free space. Yeah, I have to write the vector thing because like you know it's nice if you kind of have to. I think you should understand which quantities are vectors and which quantities are scalars. Yeah, mu naught I over 2 pi r. So that's that. And for solenoid or loop, curl your fingers around in the direction of current flow. The thumb will point in the direction of the B field. So for if let's say we have a solenoid, uh if let's say we have a solenoid and the current flows this way and it curls in, then you see how it curls downwards then up? Then you'll see that the B field will go this way. Right hand grip rule. Right hand grip rule, you don't need to know. Yes, because technically, right hand grip rule is not the only way that you can get the direction of the field. You can also technically use Biot-Savart law and then bash the cross product. So that's that. But then, yeah, so they won't ask you about the hand sign and all that. They'll just ask you about the field. So you should notice that a solid current carrying solenoid produces the same kind of B field as a bar magnet. So that's that. I can't recall on top of my head. Let me derive it real quick. Wait, let me just search it up. I kind of forgot. But then you don't need to know it because it's derived from calculus. So so then if you saw magnetic field by solenoid, yes, then you get mu naught NIL. You Then you got mu and I. Yes, it's not in syllabus, so but this guy's curious, so I'll satisfy him. Well, theoretically it is a concept. Yeah, but they don't ask you for quantitative calculations. Yes, you don't. Yes. So then that's that, and I think that's all for D1 HL. So D2, I'll now go to some no, D1 SL, D2 SL. Fuck. Hmm? Fault and cross. Oh, I see. I see. Okay. Yeah, thanks for reminding me that. Yeah. So now we'll do some questions from RV real quick. So, yeah. So I'll be really quick with this. So I'll just skip to media because I have faith in all of you. Uh, don't talk about magnetic force yet, but then I am kind of CP. We'll continue tomorrow. Nah, tomorrow I might do D4. Oh wait, by the way, one more thing. I'm very sorry, I forgot. There's one more thing that you have to understand is that about electric fields. One more thing, electric field inside conductor is 0. Understand it. Understand this, and then like we'll do some questions now. So, there's very limited SL stuff for. Okay, let's do this one. So let's try this one. This question. Yep. So let's do this question first. So please give it a go. I'll also do it with you. I'll explain magnetic force later. Can we please focus on this? Give it a go. So this is a worded question, so it shouldn't take very long. Just take some time to get the physical picture. Oh, thanks for saying. Thank you. Thank you, brother. Yeah, but yeah, nanocoulomb, but then it's not that. Yeah, but it's not important. That's not or whatever. So should be D. So I'll now draw a diagram to show you what happens. The physical picture. So here we have a positive charge, and here we have a less negative charge. So at this point, the key to this is to employ the superposition principle, right? So I talked about it a while ago. So the superposition principle, you look at the field from each individual charge and they should add up. So here's a positive charge. So for there to be zero field, there should be the electric field should cancel. So when you have a positive charge, the field goes this way. So there's a field vector that comes from the positive charge. And the negative charge, there's also an E field coming from a negative charge. And E plus should equal to E minus. So because this point is closer to this point, the negative charge than the positive charge, then for these two then so for 1 over r squared for the negative charge will be greater. So which means that the negative charge will be smaller in order to produce the same field strength. Sorry if it's confusing. I'll say again. Onto the superposition print. Maybe the RV Marsky will do a better job. Yeah, so just take some time and look at this, and then like I'll do one more question, and then maybe on magnetic field, and then move on, because I trust that all of you know how to press a calculator. Depends on calculator. Okay. So the 20 nanocoulomb charge is fixed. So then charge X will be negative. Yes. Okay, so yeah, so it's D. And I think so is everything clear? Yep, okay. So I'll look at one magnetic field question and then move on. Oh, actually, let's have this question first because Yes, this is being recorded. So let's have this. Let's do this question first because this tests your application of the principle of superposition. Patrick, hide your answers in spoilers. Thank you. Put two. So we get some C's, some D's, mostly D's. So I'll wait for everyone to finish. Okay, so mostly C or D. So I think it should be D. Yeah, because look at person. Yeah, so I think this diagram illustrates it quite clearly. Like if you just use the superposition principle, yeah, if you draw the electric field from the individual charges, then and add up the arrows, then you. So for example, you see that this charge and this charge have a symmetry, so their fields cancel. And then this pushes it to the right-hand corner. This attracts it to even more the right-hand corner. So the resultant field will be just to the right, upper right corner. So is everything clear? It's just adding. So yeah, so for as a tip, so I'll just have it right. As a tip, so tip so I'll just add here as a tip, right? As a tip, what tip when doing field questions involving multiple charges. Try draw out the field vector from each individual. Orko was saying yes, there will be no. Would there be a magnetic field? No, because the charges. If the charges are not moving, then you won't get a magnetic field. So if all the charges are same and have the same sign and magnitude, then there will be no electric field in the middle because by symmetry, yes. So I'll move on now. I'll go to I'll try find a magnetic field question and then move on. There's so little magnetic field questions. Yeah, okay, whatever. Then I'll go straight to lecture. I'll go straight to the HL content because it's 1:30 a.m. because and like I'll trust you with the calculation questions and maybe if I have time then I will talk about I'll just do some questions with you all. So for D2HL it's relatively simple. So the first thing you want to know. Yep, so for D2HL the first thing you want to know is that the concept of electric potential energy. So it's the same analogy as same. So it's the same analogy as gravitational potential energy, defined as the work done needed to assemble the charge system. Basically, it's so and you need you technically don't really need to know this, but then you should understand that the electric potential energy is stored in the electric field and shared in the system. So, and as a formula, right, then equals to AQQ over R. Yes. Again, K will change if you have a medium with a different relative. Yep. And also keep in mind that um mind the sign of the electric potential energy. So what happens is because when you so for example, if you try to assemble two protons together, then what happens is first you have a proton here. Then if you try to bring another proton, there's an electric field. It's repelling the proton. It's repelling the proton, and therefore you need to kind of push it. You can't need fuck. You can't need to push the proton. You need to do work to kind of push the proton near the other proton, and therefore the electric potential energy is positive in this case. Yes. Yes, and two electric potential. Again, it's the same concept as gravitational potential. So we want to try and come up with a quantity that is dependent on only one body. So defined as charge field. Um V is equal to KQ over R. And you can also say that is equal to negative and you can also then say that negative um and that same as gravitational fields, electric field strength is the electric field is the negative gradient of the electric potential. And so what happens so and say and basically same principles as gravitational potential energy, but this time you need to watch out for the sign. And then just some more equations that is that work done is needed by is equal to Q delta VE. Yeah, and the third one is equipotentials. This is then it is the same concept, same as gravitational field. Too lazy to explain further. Okay, so now I will go through a longer question for D2 HL, and then I'll move on to, and then like I will play a game of GeoGuessr and move on to D3. So let's do. All the questions are super long. What the fuck? Okay, screw a longer question. Let's do some shorter questions now. Okay, I'll randomly choose one. This. Okay, let's do this one. Yes, I play poker, but not a lot. So let's do this one first, and then like I'll do some. Yeah, and then I'll do the oil one. So we'll do some MCs because all the long questions here are super long. I'm not aiming to play a multiplayer game. Sorry. Uh, yeah, so just give this question a go, chat. Sure, you can send it. So Rack, I think this is just essentially testing your definition. So I think yeah, I agree it's B. I'm not sure, but then I don't really trust my brain at 1:30 a.m. So yes, it's V. It's B. Yeah. So it's just defined because yep, delta VG is the amount of work needed per unit mass. So you just multiply by mass to find the work done needed. Then delta VE is the work done needed per positive charge. So when you have a negative Q, you need to multiply that in, so you get a negative Q there. So that's that. Now I'll go. So Patrick requested we do an oil one. This one? Wait, sorry, chat. Sorry, chat. My Discord is. Sorry, chat. Discord is trolling. Oh, my Discord's. Oh, my Discord is crashing. This isn't good. Uh. Oh. Actually, I got. Yep, all good now. So yeah, so give this question a go, chat. I haven't done this before, so I'll also do this. Give it a go, and then maybe one more question, and then I will take a break. Seems like everyone's dead. Okay, I'll draft it. So I got C, and yes, it's C. So what you want to do is essentially you want to use the parallel plate formula, right? That E equals to V over D, and then equate mg equals QE, and then substitute back the expression. Yes, exactly. So then you end up getting this. Yes. Yes, Patrick, correct. So parallel plates is nice because you have a nice uniform electric field that has constant magnitude. So I'll have one more question. Hopefully, is I'll try to find a harder one. Discord crashed again. Oh, never mind. So okay, let's try this one because this is about energy. We got guessing here, right? Don't do that. As it's not reliable. Come on. Okay, so let's give this question a try. So think of it in terms of electric. Think of it in terms of potential energy because you did get given the potential difference. And pay attention that now you have an alpha particle and not a proton. Proton. I think the trick is realizing that proton, the difference between proton and alpha particle. Alone. So I haven't answered myself, but I don't trust myself. Aloha. Okay, so because there's so little people in here, I'll just go. I think it's A. Yep, it's in. Fuck, I beat down my own glasses. So anyway, what happens is you should understand that the trick in there's a multiple key points to make. No way. First of all, is that you don't care about the distance because you look when you have anything to do with velocity, you look at the kinetic energy. Yes, so you only need to care about the potential difference because that's what controls the energy. So d over 2 or d gives the same electric potential energy. That's the first point. And second of all is noticing this sentence. Is that noticing a discrepancy between an alpha particle and a proton. So that is the other thing that you do. And then EV is because you have a EV is proton has charge E accelerated across potential difference V, then gets energy EV. So that's that. So I'll just take some time to read it if you didn't get it right. And I'll have another game of GeoGuessr before starting D3. Bye-bye. Bye-bye, Rack. Okay, so enjoy one game of GeoGuessr. Looks so American, these houses. These look so American, but where? Looks depressing as fuck. How? Thinking less. I don't know. I still have a it's probably in though. Looks a bit uncivilized. I'll go to the new order. Whoopsies. No, Thai has a different language. This is the expertise from the other. I'm not sure if it's Paris. I'm guessing. I'll guess Paris anyway. Something tells me it's South America, but let me have a closer look. We'll see. For fuck's sake. Oh, it's the Southern Hemisphere. Hare. Yeah, but then like this part's also dry. Probably some rich, probably some rich part in South Africa.有一说姐姐王。Gut feeling. Yeah, I swapped those two. One more game. Oh. Yeah, please. No, the sign was in green, that's how I knew it. Hard to tell. good. Sorry, I don't know how to check number of plates. My bad.
Tinapangkan de Makati.
Oh, not India. I think. Indonesia is so annoying because there's so many different islands. Yeah, nice. Oh my days. Oh my days. Oh my, America guesses are so off today. Oh fuck! Oh, yeah, again. Yeah, maybe this is a sign I shouldn't keep playing. Okay, guys, let's come back for. No, let's get back for B3. No, D3. Oh, okay, D3. So if you're SLHO, listen up. D3. After D3, I can see. So D3 so D2 basically looks at the electrostatics and the magnetostatics, right? But D3 it basically looks at electrodynamics, motion in EM fields. So D3 is approximately split into two parts. The first one talks about motion in electric fields, and second one will talk about motion in magnetic fields. So as a while ago, as discussed a while ago, we know that charged particles experience of force in electric field. By Newton's second law, this implies that they become accelerated. So then in particular, right, if we use F equals ma, then we get ma equals to qe. So some of the simpler cases I will go over. So one slightly more interesting case is that you can set up an equivalent projectile motion in the in a uniform electric field. And what do I mean by this? So when you have a cell, so let me just erase everything. So if you have an electric field pointing down, and you have a positive charge initially going in there, then as the positive charge goes in there, it undergoes a downward acceleration, right? Because F equals QE. So that it kind of accelerates down and goes a projectile motion like how a mass on the gravitational field undergoes projectile motion, like what you do in A1. So yeah, so I've seen quite a few questions being posted in the physics channel, so I thought I'd explain this. So the electric field points down. Oh, we lost. later. Sorry, Dreams. Yep. So that's about it. And for energy, then you can just say Ke equals to 102 mv squared equals to Q delta V. So that's what kind we did a while ago. So just remember that for energy and velocity calculations, you kind of look at the overall potential change. Whilst if you're looking at force acceleration, then you look at field. Right, for force. Potential. So that's that. An electric field, I think, is quite simple. So, and now we're talking about magnetic field. So now, Dreams, I'll answer your question. And yes. Oh, oh, I messed up all the formatting. Sorry. Okay, there we go. So magnetic fields. So first of all, we want to know that is that magnetic fields exert a force on charged particle. The force is perpendicular on moving charged particles. The force is perpendicular to both the velocity vector and the magnetic field. And so, Dreams, you're right in saying that, yes, in the case of perpendicular. So, naively, we'll say that equals to QVB if the velocity vector is perpendicular to the B field, which is most cases. But then if not perpendicular, then we want the perpendicular component only. So then in that case, then we'll have equals to QVB sine theta. Or if you do HL math, then you also know that if you do HL math, you also know you can see this as a cross product as well. So Q. So for those who don't know cross products, how do you determine the hand sign? So for this one, you can to determine the direction of the force, you use the right hand slack rule. Yeah, and one important thing is because magnetic fields exert a force that's perpendicular to the velocity, you should understand that magnetic forces do no work. So in my mock paper, I had a trick question which asked about the work done by magnetic force, and if you know this, then you should answer this in 10 seconds. But then for those who don't know, then they will do a lot of calculations just to get it wrong. And so when you have a force perpendicular to velocity, then as Dreams said, for a charged particle entering the magnetic field, it undergoes circular motion. That you're correct in saying that. if V perpendicular to B, then we can equate the centripetal force equals to QV to B, which then gives us R equals to mv over QV. Yeah, so just as a application, right? Let's say we have a magnetic field. Just as an application, I'll just talk about mass spectrometry real quick. So let's say we have a uniform magnetic field pointing into the page here, then have a positive charge. Then using the right-hand slat rule, actually no, we haven't. So we have a positive charge. Let's say we have some field pointing in out of the page. Then we have the F exerted this way. Oops. Bro. So then it'll bend this way, right? So let's look back at the expression for the radius of the circular motion. So it depends on the charge of the particle, and it determines the mass and velocity of the particle. So in mass spectrometry, how they determine particles of different mass is that they make the particles have the same charge, they have a uniform magnetic field, and they accelerate them across the same potential. So V is the same. So but then the mass is different, so then the radius is different. So when they when the particles are passed through, some have a larger radius than others. So they I think they probably place a screen on here, and then when they hit different places, then you know that they correspond to different masses. Yes, correct. I don't know why the emoji was there, okay? But yeah, just here you go. Um, and let me see. And I think one more extra thing you want to know is that there is one called, and I think one more niche thing that the IB wants you to know is that when when there is an E field perpendicular to a B field, there is a certain value of E which will make the charged particle undeflected. So what it means is that let's say we have um let's say we have um let's say we have a magnetic field and we have a proton entering. So magnetic field enter the plane, so then the proton should get a magnetic force up. However, if we have an electric field down, then it'll also have an electric force, and there should exist one E field value such that the electric force will exactly balance out the magnetic force, and the proton will then just travel in a straight line. So we have then Q equals to, actually no, sorry, it should be a certain value of velocity. I'm sorry. So this is also nice to know. Actually, where are all of you from? Because like, oh, is everyone Asian here or what? I see, fair enough. Which formula? I think they meant like the R this formula because it can kind of help you hack through it really quickly. Yep. So that's that. I think that's enough for electromagnetic forces. And one last thing for D3 is magnetic forces on current carrying wires. So as you know, right? So how I like to look at this is that how I how I like to look at this is that a current carrying wire is basically a bunch of moving charges. So by looking at one moving charge in the field, we can deduce the overall direction of the force on the wire. Then you can say the force's direction can be deduced by Fleming's left-hand rule. This direction is yes. So like currents attract and different and opposite currents repel. I'll illustrate that later, but I'll just talk about it first. Oh, Fleming's left-hand rule, and for an equation, right? I'm gonna say that um equals to BIL prime theta, or if you do then you if you do HR math, then we can also do I L cos. Yes, then you can also do this. Yes. So that's that. It's just Fleming's left-hand rule. It's not that complicated. And for two, current carrying wires, the force per exerted per unit length can be described by F equals to mu naught or I1 I2 over 2 pi r. Combine the derivation is just combine like currents attract and opposite current repel. So the derivation is just combine the equation B equals no I over 2 pi r with bi with oh, yeah. And just to illustrate why like currents attract, it's good to kind of sketch out the field lines to see like what happens. So I'll just show one example of like currents because that should be enough. So let's say we have one current carrying y here, and by right-hand grip rule, you have a magnetic field that's into the page, and we have another current here. So using Fleming's left-hand rule, I is going this way, B is going inside. So then I cross B should go left. Using Fleming's left-hand rule, right? FBI. So F should point to the left, which shows that it's attracted to the wire. Um, 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 and here's a tip. For these situations, try sketching out the magnetic fields. Might be useful to deduce the direction of our resultant. Of course. Yeah. Yes, I will send out the word. So yeah. So I think that's all for. Wait, can you all hear me? I think my AirPods died. Okay. So I'll keep going. So anyway, I think that's all. So I'll go through some questions and then I'll end the session. So I'll just go. I'll just hop on. Can we do this question? Let me. The problem with Discord right now is that the horizontal component on my. Wait, AIX, can you send it in M25 physics? Because what happens is when I try to open the image, my Discord gets incredibly laggy. Okay, so the horizontal component of the Earth's magnetic field near the equator is 30 microteslas. A cosmic wave photon, it arrives into the field with vertical velocity of 2.8 times 10 million. I feel like my computer's gonna overheat. Property for photon. Okay. So it's just essentially asking you to do balance QVB and MG. So because because um because you know the because you know the mass of a proton and you know G. So just open, yeah. Okay, so actually I won't go over questions because I think everyone's tired by now. So just as a final remark, to answer this question, find the magnetic force by doing QVB, and find the gravitational forces by doing MG because you know the proton rest mass and you know G, and then it's a proton, not a photon. Yeah. So then you'll get it. Yeah. So there you go. And sorry for abruptly ending it, but thanks. Nice to have you all. I need to sleep now, and my computer needs to take a break. So thank you all for staying for 3 hours. And yeah, and I don't know if I'll host D4 tomorrow. I might or I might not. I will I'll think again, but yeah, I'll settle on a D4 soon. But then if it's D4, then I'll probably the same time tomorrow. Yep. So yeah, thank you. For those who are Asian, then good night. If it's gonna happen, don't ask me. You ask me, I ask who. I need to pan Lisa. I don't know how much REM. Good night, everyone. Thank you. Bye bye.